Hey, now we're about to start one of my favorite chapters because I like messing around with magnets. And what I think is cool, we just finished talking about electricity and now we're moving into magnetism. Here's what I think is cool. Electricity can make magnetism, and magnetism can make electricity. These two forms of energy can each create the other one. I think God knows what he's doing. Well, let's learn a little bit now about magnets and magnetism. Here we go. You see a picture of lodestone. Now I have one, but it's not very strong as far as a magnet goes. These stones have tiny little iron deposits inside them. I'll tell you in a minute what all that fuzzy looking stuff on the outside is. Notice that says used as a compass needle. Many centuries ago, navigators didn't have compasses to find their way around like we do now. And of course, what we have now is computerized. But they found tiny little pieces of rock that always seemed to point toward the north in the northern hemisphere or the south in the southern hemisphere. And had to figure out why. Turns out that the Earth has a very large magnetic field and is actually one great big magnet. This naturally occurring magnetic rock is called lodestone. And the reason this rock is magnetic is because this rock contains little tiny iron deposits on the inside. Iron, remember element 26 is iron, the Latin name is ferrum. So iron is one of three ferrimagnetic materials. And iron is inside this rock called lodestone. Tiny iron deposits on the inside. And iron is very strongly attracted to magnets, which is what that word ferrimagnetic means. It's really pronounced ferrimagnetic. But lodestones were used as the first known compass needles because they were the first known magnets. And we're talking many centuries ago. Of course, we have all kinds of magnets now with a whole lot of uses for them. And we'll talk about some of those uses as we go through this chapter. Ready? Magnetic poles. I mentioned a moment ago that the Earth has magnetic poles and is actually one very large magnet. More about that coming in a little bit. A magnetic pole is the area of a magnet where the magnetic strength is the strongest. So two areas of a magnet with concentrated magnetic force. Every magnet has two poles. You will never have a magnet with only one pole. And we call those north and south. Okay, just think of the Earth, north and south. But there's a twist to that when talking about the Earth. And again, we'll see that in a little while. But that's simply what they're called because one end of the magnet always seems to point north when dangling from a string, and the other magnet always points south when dangled from a string, the other end of the same magnet. So the poles are called north and south. Now, if you break a magnet into two pieces, you will not get one magnet with only one pole, such as the north, and a different magnet with only the south pole. You will get two complete magnets, each one now having its own north and south pole. It's impossible to have a magnet with only one pole. Now, over many years, iron magnets will lose their strength and the poles may lose them at different rates. So you may have a north pole on one magnet that is stronger than the south, or vice versa. The south could be a little stronger than the north. But there are going to be 2 points on every magnet, and those 2 points are stronger than the rest of the magnet. And those 2 points are called the poles. The shape of the magnet and what we call the magnet, that's determined by where the poles are. Ready? Here's a law of poles. Now you see the picture here. I'm not sure in the picture if blue is north or red is south or what. Let's just call blue north and red south. Notice that when we put a north with a south close enough together, you see this attractive force right here. These magnets are going to stick together because of that force. Now look on the right side. If we put a north and a north together, or really, let's say that was a south and a south together, you see how the forces repel each other. We're going to do an activity that will let you see that with real magnets and real iron filings. That fuzzy stuff that is on the picture of that lodestone, that's iron filings, tiny little pieces of shaved iron. Here's your law of poles. Very, very, very similar to the law of electric charges. Remember, we talked about static not too long ago. Like poles repel. Put two magnets, the same poles of two different magnets together, those magnets will not stick. And if we get two strong magnets, we'll be able to feel that repelling force. Now, you can't see that just by looking at a picture on the screen, but we'll do that with some real magnets in class. Like poles repel, unlike or opposite poles attract. So if I put a north next to a south, these two are going to stick together. And again, if we get a strong enough magnet, we don't even have to put them all that close together. Once the magnets get inside the field of a magnet, they're going to stick together. So strong magnets are really good at showing that like poles repel and unlike poles attract. That's the law of poles. Ready? Now, magnetic field, I mentioned this a couple of times already. See the bar magnet right here. And all this, these are iron filings. It's like this. If to burn the toast in the toaster, some people will take a knife and kind of a butter knife and just scrape off those burnt crumbs, I guess you'd say. Well, that's kind of what happens to get these iron filings. It's done more by machine though. Take a piece of iron and run that through a machine and have that machine just scrape off little pieces, tiny little pieces, until we get powdered iron, and we call that iron filings. I do have some that we will use in class. The magnetic field is the area surrounding the magnet in which the force acts. So all this area, you see how the filings are kind of lined up in a nice, neat little pattern, especially closer to the magnet? That's the magnetic field. We get filings outside the reach of the magnetic force, then those filings are just going to drop randomly and not have any pattern to that. The magnetic field is the area around the magnet in which the strength actually acts, the force. These lines of force will show the strength and the direction of the magnetic field. You see it in the picture right there. Hopefully that picture shows up well on your screen, but we'll see that for real with an activity that we'll do in class. Magnetic field, though, the area surrounding the magnet in which the force acts. Ready? Now, the Earth is one great big magnet. This got discovered quite some time back. You've heard of the North Pole and the South Pole, obviously. Now, how many of you already knew that the Earth actually has two North Poles and two South Poles? And those poles are not in the exact same spot. One North Pole is called the geographic North Pole. That's where Santa lives. The North Pole, and he makes all the toys and flies around the Earth for Christmas. Yeah, right. And the other one is called the magnetic North Pole. You're going to see a picture in just a bit. And the same on the bottom. The South Geographic Pole goes from the North Geographic Pole straight through the center of the Earth and out to the South Pole. There's also a magnetic South Pole as well. Now, the exact locations of the magnetic poles shift extremely gradually every so often, maybe every few years. And right now, they're approximately 470 kilometers apart, the North Pole geographically and the North Pole magnetically. But those can shift. You ever looked at a globe and noticed that the globe is tilted? And that's because the Earth is tilted. Well, what makes the Earth magnetic? There are three metals that are very strongly attracted to magnets: iron, cobalt, and nickel. On the periodic table, iron is element 26, cobalt is 27, and nickel is 28. Now, inside the Earth, the very center of the Earth, we have molten iron, liquid iron, above the melting point for that metal, and molten or melted nickel mixed together. And because the Earth continues to rotate, then those two metals will stay melted into liquid and therefore cause a very large magnetic field that reaches miles and miles out into outer space. Here's another example of God knowing what He's doing. This magnetic field of the Earth will either repel or trap charged particles that come from solar winds. very dangerous solar winds out in outer space, and those particles could destroy life on Earth. But just like God put an ozone layer to block the harmful highest frequency rays from reaching the Earth, there's also this repelling or trapping magnetic field to keep those charged particles from hitting the Earth and destroying life. There again is evidence of God's creation and God's ability to protect life on Earth. But the Earth itself is one big magnet. And again, a picture is coming up. Ready? And there's a little picture of it. It's not, actually the Earth, but you get a little diagram on here. Now I want you to notice something. The geographic North Pole right here at the top, and the geographic South Pole right here at the bottom. The magnetic north is shifted over a little, and so is the magnetic South Pole shifted over a little bit. But look at the diagram of the bar magnet that is representing to extend through the Earth. There's a North Pole down here. There's a South Pole up here. But that's north and that's south. What? Well, let's remember something. The magnetic field of any magnet comes out of the north end and goes around the magnet and into the south end. And that's the same with the Earth. With the Earth, the magnetic field comes out the bottom of the Earth, extends around the planet, and back into the north, the top of the Earth there. So by definition, these names are actually backwards, since the magnetic field of all magnets flows out of the north end, around the magnet, and back into the south end. This is actually a north magnetic pole, and this is actually a south magnetic pole. So why do we call this magnetic south and magnetic north? Well, it's supposed to be to avoid confusion. But by definition, the Earth's North Pole is actually down south, and the Earth's South Pole is actually up north, but we change the names to match the geographic. That takes some getting used to. But the North Pole of the Earth's magnetic field is actually a south, and the South magnetic pole is actually a magnetic north. Takes a little getting used to, strange, but that is the case. Ready? I mentioned the word ferrimagnetic earlier. This is ferromagnetic metals. These are strongly attracted to magnets. I could have possibly said that wrong earlier. Oh well. Ferromagnetic. Remember, iron is ferrum, and iron, cobalt, and nickel are the strongest metals attracted to magnets. They're called ferro. And there you see again, iron, remember symbol Fe, nickel, symbol Fi, and cobalt, symbol Co. And they are right next to each other in the middle of the periodic table in period 4. Now, all metals have a melting point, but think of something a little similar when relating to the magnetic strength of a magnet. If we were to heat up a piece of magnetic iron to the certain point called the Curie temperature, that magnet may stay a solid, but that magnet will lose the magnetic strength that it has. And for iron, that's 770 degrees Celsius. Now, I don't know the temperatures of nickel and cobalt, but the Curie temperature for iron is 770 degrees Celsius. That's a very high temperature, and at this point, even if iron is very strongly magnetized, that particular piece will lose its magnetic force. Ferromagnetic metals are metals that are strongly attracted to magnets, and there are 3, iron, nickel, and cobalt. Now, there's a metal called neodymium. That is element number 60, and that itself makes a very powerful magnet. And we can buy those at hardware stores. And those neodymium magnets, they can be fun to play with, and they're extremely useful in appliances, such as washing machines, because those kinds of magnets hooked up to an electromagnet and combined with one of those, we'll talk about that a little later, those allow things like the tub in the washing machine to spin around. So neodymium magnets are also very powerful. But ferromagnetic metals, iron, nickel, and cobalt, may not be magnetic themselves, but those 3 metals, they can easily stick to strong magnets, and they could be magnets themselves. Ready? Paramagnetic metals. These are very weakly attracted to magnets. So we have ferrimagnetic. That's a naturally occurring piece of lodestone with iron inside. Ferromagnetic. Those are iron, cobalt, and nickel with very strong attraction to magnets. And now we have paramagnetic. Aluminum, a good example. These metals are very weakly attracted to magnets. Normally, an aluminum can will not stick to even a strong magnet. The magnet would have to be very, very strong in order to get something like an aluminum can to stick. Otherwise, normal magnets that you're going to mess with in daily use, now aluminum and most other metals are not going to stick to those very well, if at all. That would be paramagnetic, a weak attraction. So many times we'll see shows, TV shows or something, and just say, will the metal stick? And they say, get a metal and use a magnet. Well, it has to be one of the three ferromagnetic metals, iron, cobalt, or nickel. Because aluminum, tin, copper, calcium, those metals are not going to stick to magnets very well at all. Ready? All right, we are almost done with this. Now, what makes something become magnetic? Think of an iron magnet. Well, remember, electrons are tiniest pieces of material, and they all have teeny tiny itty bitty little magnetic fields, and we call those domains. And we get a whole bunch of atoms together. All these electrons are spinning around in different directions. You get a whole bunch of these electrons together, we call those domains. Now, in most materials, all those domains, as you see here, they're all randomized, facing many, many different directions. Therefore, all their tiny little magnetic fields, called magnetic moments, end up canceling each other out. But in magnets, notice the perfect arrangement and alignment of all these domains lined up in series, straight across and next to each other, all facing the same direction. Okay, so you got north here and south over here. So you got a tiny little north and south, tiny little north and south, and so on all through. Now, turns out, run electric current around a piece of iron, and all these mixed up domains will suddenly become magnetized, because all of a sudden, with enough electric energy, all those domains are going to line up. That's called an electromagnet. But domains are really tiny regions inside the metal, and you put a few of these domains together or regions together, you get what's called a domain, and you put a whole bunch of domains together and line them up all in the same direction. Electricity is a great way to do that. Well, then you have a magnet. Electricity, though, isn't permanent, because once the electricity stops flowing, then the magnet loses its strength. Permanent magnets have these things constantly, permanently aligned. Over time, though, it may take many, many years, the magnet's going to lose its strength, because eventually those domains will start mixing themselves up again. So when the domains are randomized, the magnetic fields cancel each other out, so there's no net magnetic field. But line them all up, like on the right side of the picture, we have magnetic fields that build and build and build and build. See, it's like the opposite of what we said a little while ago. Break a magnet into two pieces, we get two tiny little magnets. Well, then break each of those pieces, we get four tiny little pieces, and so on and so on and so on. We end up with a whole bunch of teeny tiny little magnets. We'll do the opposite. Stick all those teeny tiny little magnets together, and we eventually get one large magnet. And that's all because domains, and domains are electrons. They're all lined up in the same direction. Ready? Many magnets are permanent, many magnets are temporary. And temporary magnets, such as electromagnets, can be extremely useful. All right, there are a few ways to make something temporarily magnetized. Temporarily, I was trying to say. And the process is called induction. When we take a piece of iron or cobalt or nickel and we temporarily magnetize, meaning the strength is going to go away soon. Here's one way. Attach a piece of iron to a magnet. I can definitely show you these three ways in class. Attach a piece of iron to a magnet, such as a paper clip, which is made of steel, and steel is mostly iron. It's iron and a little bit of carbon. But if you stick a metal steel paper clip to a magnet, that paper clip temporarily becomes magnetized. Now, carefully remove that paper clip from the magnet, and that paper clip will stay magnetized for a short period of time. And I'll show you all this in class. This one I have a little hard time doing, but it is very possible. Take a piece of iron against a strong magnet and scrape that iron many times in one direction, maybe a few dozen times in one direction. Take an iron nail or a paper clip, scrape against a strong magnet the same direction, maybe 20, 30 times, and you may get that piece of iron, that nail, to pick up some paper clips. And those are on a small scale. Of course, larger ones can be used for different reasons. Run electric current through or around the piece of iron. Think of junkyards and the large electromagnets that pick up the cars, move the cars, and then drop those cars. Well, someone in the driver's seat of that crane, all he does is turn on electricity. Electricity lines up all those domains to get a very strong electromagnet, picking up the cars, which have a lot of steel in them, move the cars to a different place, and turn off the electricity. Okay. We can do that if we have battery, copper wire, a battery like a 6-volt battery, and some paper clips. Okay. And as long as everything's working correctly, I can show you how to make a small electromagnet. But we can temporarily magnetize pieces of iron, especially, but iron, cobalt, and nickel, and make them magnetic. But once we turn off the electricity, or numbers 1 and 2, they're not going to last that long. Ready? Oh, we're done. I thought we had another page or so. Well, hope this lesson magnetized you because it has a magnetic personality. See you next time.